Rainer Dumke is a professor at Nanyang Technological University in Singapore. So he's also a principal investigator at CQT, Center for Quantum Technology, Singapore. His research focuses on quantum circuits and the quantum sensors. So in the last years, he has been working with quantum networks that include atomic as well as superconducting platform, and is steered toward hybridization of these two technologies with potential applications in quantum computing. So please, Rainer.
Yes, thank you. Thank you for the nice introduction, Luigi. And also thank for all panelists staying up so late, at least here in Singapore. So maybe, so in this talk, I would like to sort of emphasize on, let's say, two quantum systems, atomic quantum system and superconducting quantum system, and actually how to bring them, or if it's actually possible to merge them together. Maybe let me also share that, let's say, this work was, of course, not possible without my team, where we have, let's say, Christoph Hufnagel, Ranger, and Jaap, who are working on the superconducting part, as well as Farshad. Feng En working on an atomic experiment, the calorimeter, and then Kun Xiang actually, probably also in the audience, working on the Atomtronics experiment. For this experiment or this research, we have strong collaborations with the team around Luigi, Craig, and Tobias, and are continuously progressing this area. Okay, so let's start. So if you look now, what are, let's say, the major quantum key technologies, at least from my perspective? There are, of course, neutral atoms, which actually form very, very nice quantum mechanical systems. I mean, it's most nature given. You have your nucleus, some electrons around, and this is a very good quantum mechanical system. And I don't have to probably emphasize the power of neutral atoms in this audience. Then, of course, we have trapped ions, photons as well. There are also various key experiments were actually shown in. And of course, let's be more recently compared to neutral atoms and trapped ions, superconducting quantum circuits have emerged. We actually know how to couple these various systems around this corner here. So we actually know how to couple neutral atoms with trapped ions. There will be quite a few experiments where neutral atoms and trapped ions were trapped in the same space. We know how to couple photons to ions or to neutral atoms. But what is a little bit lagging behind is the coupling between neutral atoms and superconducting qubits. That's actually very important to actually couple these two advanced quantum systems together to form actually more diverse quantum mechanical systems. And that's what we are talking about. Of course, there have been already some previous experiments using some superconducting systems, not necessarily qubits, to couple two neutral atoms in the group of Doris-Bortmann. Maybe first, let me talk a little bit about atomic quantum systems. So as mentioned before, they have a very nice internal structure, as shown here for rubidium-87. One can, let's say, if one thinks about qubits, say one uses, let's say, the hyperfine ground states as the qubit states, and maybe go then to higher excited states for interactions. The external degrees of freedoms we can control very well, and cool the system down to reach Bose-Einstein condensations. And with this, actually, oh yes, we can also introduce, let's say, light fields to couple to the external degrees of freedoms to the ends. We can make trapping potentials. Also with gradient magnetic fields, this is possible to do so. Shown here because they have, let's say, certain atoms, in this case, for example, alkali atoms have a magnetic moment which you can actually grab on and generate magnetic potentials. What we can actually do with this, let's say, atomic systems is we can actually build sensors. For example, here next example, one of our experiments, we actually realized a atomic gravimeter system, portable atomic gravimeter system. The idea here is fairly simple. So we start with either cold atoms in the range of about a microkelvin, do a velocity selection, and then have three light pulses, one a beam splitter pulse, a mirror pulse, another beam splitter pulse. And after a time of flight of about 300 milliseconds, we can see the interference pattern. The system is actually shown here, and it is actually portable, so we can actually move it around and do, let's say, measurement of local gravity at various places at a accuracy of about 10 to minus 9 G. And the full system is actually also fairly flexible because it's just controlled via a computer through the cloud. So there's no need that there is a PhD student tuning the system. But still, it is not very compact. And that's what we are looking in on later. Another, let's say, quantum sensor, which we can actually build from these atomic systems, are, for example, magnetic quantum sensors. The idea here is the following, that we actually use, in this case, the magnetic moment of the atoms and align this, or if we now apply a magnetic field, this magnetic moment will precess around applied magnetic fields. And this precession we can actually detect with or we can detect with looking at the polarization of a interacting laser beam. And this system, we can actually achieve sensitivities in the range of about 14 femtotesla per square root hertz. This we can also use actually, since it's a decently compact setup, as it's actually shown here. We can actually use and apply it. What we have done is we have used the system, the atomic magnetometer, to actually measure, or let's say to apply in magnetoreception of animals, where we actually used in this case an American cockroach and looked at the, let's say, magnetic response of the American cockroach to actually rule out, let's say, certain models. In this case, the model due to small magnetic particles inside the American cockroach. The idea there is that sort of inside this insect, there will be small, let's say, magnetite particles, which align to an external field, and the, let's say, animal can actually see this or somehow sense this type of alignment. But the measurements which we have seen is measured is that this alignment of this small magnetic particles would take a time scale of up to hours, which is actually not useful for, let's say, navigation or magnetoreception. And in fact, actually, since we have done this with cockroaches, and we also have seen a difference of this alignment between dead and alive cockroaches, for this we have received in 2019 the Ig Nobel Prize. Okay, so I've shown you that, let's say, with this atomic systems, we can actually build very powerful sensors. For example, in order we have built gravimeters and magnetometers, but they are portable, but they are not very, very compact. So the idea now is to, let's say, try to shrink down the system size by using Atomtronic elements. And one possibility, for example, is to use very small, or let's say, miniaturized magnetic traps. What actually we are doing is we use, in this case, superconducting, let's say, a small YBCO sample, type 2 superconductor, apply a magnetic field inside this superconducting thin film. And what we actually see is that vortices will penetrate inside this film. And if we then decrease this magnetic field again to 0, the vortices will remain inside this film. This vortices will generate a magnetic field, And this magnetic field we can actually use to trap and manipulate atoms. It is shown here, where we can actually levitate atoms above a small superconducting YBCO square. This, let's say, YBCO square is filled with vortices in a certain type of pattern. What we can actually do is we can shape this pattern by using a arbitrary shaped light field, using in this case, a DMD, as is shown here, shining in with a laser beam on the DMD, and then imaging the image from the DMD to the chip surface. We can generate various vortex patterns by just deleting certain vortices in the thin film. And with this, we can, let's say, generate various patterns, as it's shown on the right side here, for example, two lines in the most simplest case, but also it's possible to generate a ring type of patterns, which we have done. Another possibility to actually, let's say, miniaturize atomic circuits is to use, instead of magnetic fields, optical fields. So in this case, we have set up an experiment where we use, similar to these experiments which were shown in previous talks, where we have a BSC in a 2D sheet and shine on top of this a pattern potential generated by a DMD. And also here we actually could trap, in this case, let's say a BC in various types of shapes. And trapping them in this various types of shapes, we are currently in the progress of looking at, let's say, doing various experiments which we have worked on theoretically before. For example, loading these atoms, or let's say shaping the atoms in a ring type of pattern, where we hope to see some interesting behavior in the dynamics, or loading actually, let's say, the ring type pattern additionally with a straight guiding potential, where we can actually also measure the, let's say, outcome of the atoms in the straight guiding potential, depending on the rotational states of the atoms inside the ring. Okay, so this was, let's say, very briefly about the, let's say, atomic system and what we can actually do with these atomic systems. Now let's switch a little bit gear and we, let's say, investigate a little bit superconducting quantum systems. So the most, let's say, superconducting, or let's say, the superconducting, let's say, circuit, which is typically used, are just harmonic, also are just AC resonators. Interestingly, is if we actually go to very, very low excitation, this AC resonators, we see that the excitations are actually quantized. So we can actually, in fact, we can actually write down the Hamiltonian of this AC resonator. If you want to use, let's say, this type of systems for qubits, that might not be very advantageous, because all energy levels have the same spacing. So what we actually have to do is we have to bring into the system a nonlinearity, so-called chosen junction. And with this harmonic potential will become anharmonic. And with this, we can actually live the degeneracy of the energy spacing. And generate a very, or let's say, an isolated two-level system between the ground state and the first excited state. There are various flavors of qubits, depending actually which element is more dominant in the superconducting circuits. If it's, let's say, the capacitors, if it's the inductance from the Josephson junctions, or some shunting capacitors, like for the Transmon Qubit. But at the end of the day, they, let's say, behave all very similar to this, let's say, simplified picture I've shown earlier. In our experiment, what we actually do is we have a 3D cavity made out of aluminum and, made out of copper. And inside this cavity, we have placed 2 Transmon Qubits. One of these Transmon Qubits is a fixed qubit. The other one, we can tune the frequency of the Transmon Qubits by changing a magnetic field. This is the experimental setup. These Transmon Qubits are put inside a magnetic field shield at a temperature of about 10 millikelvin, 9 to 12 millikelvin. Let's say, control of this qubits comes from an arbitrary waveform generator, and then it is the signals will go down through these different cooling stages of the refrigerator, will be attenuated and filtered, and reach the qubit or the qubit system. After the qubit system, again, we have various filters and a cryogenic amplifier to amplify the signal from the qubit at cryogenic temperatures to decrease the noise, and then read it out with a ADC. Typical times, T1 times are about microseconds, 8 microseconds, T2 times about 2 microseconds. The state fidelity we can prepare the system in is in the, let's say, ground state is about 99.3%, and in the first excited state about 98.9%. For the, let's say, single qubit system, as is shown here, this one is actually inside a aluminum cavity. If we have, let's say, this 2 states, the ground and the excited state, apply a microwave pulse, we can very nicely see the, and change actually the timing of the pulse. We can very nicely see the Rabi oscillation for, let's say, various frequency tunings over time. The same, we can also look at the T2 times and apply 2 pi over 2 pulses and change the time t. And also here, we can very nicely see the Ramsey oscillations. So having this, let's say, in place, single qubit, and this control over this qubit system, it's actually also possible to test a very simple single qubit code. In this case, the truncated Gauss sums or factorization. The idea is to mimic this type of equation here by applying microwave pulses to the qubit system. The idea is that this part in the cosine, which is given by, let's say, n, which is arbitrary large integer number, or an arbitrary integer number, and L, a factor, or let's say, a arbitrary number. And if L is a factor of n, we would actually see that this value of the Gauss sum is actually 1. And if it's not, then actually it will go to 0. This, let's say, equation we can again simulate by starting with the cubic system in the state 0, apply a pi over 2 pulse with a initial phase, a random initial phase, and then apply various pi pulses with phases given by this term down here. If in this case L is a factor of n, so L is a prime factor of n, we would actually see that the signal after a certain amount of pulses will actually remain maximum. Whereas if we use for L a non-factor of n, the signal will go to 0, or let's say will decrease. And for a large number of repetition of the pulses, it will go to 0. This is only true for, let's say, certain non-factors. However, there are, let's say, special non-factors, the so-called Gauss factors, where we actually remain to see a still significant contribution from these numbers. As it's actually shown here in this graph, in the simulation, where we're doing the experiment, for example, here for a factor, L equals 28, we actually see with the increased number of pulses, the, let's say, signal will start from, sorry, the signal will start from 1, so full visibility, and then actually decrease due to the decoherence in the system. For a non-factor, in this case, a Gauss factor, also therefore, let's say very small, let's say number of pulses, it will start at a very high probability to measure it in the, let's say, particular state, and then starts to oscillate. With the, let's say, going with the increasing number of pulses. So for a fixed number of pulses, it's actually not possible to really distinguish, let's say, factors from non-factors. This is also what we measure in the experiment. For example, here we see the red curve for a factor, and the blue curve is for a Gauss factor or non-factor. But we can actually overcome the selection of Gauss factors with a post-processing of the data, which is shown here. So if, let's say, n is an even number, so the number which we want to factorize, and we can divide it by 2 until we are at an odd number, obtained an odd number. Then we store the number of divisions which we have done. If the number which we have arrived is divisible by 5, we can do this as well, and then actually store also the number of divisions by 5. The, let's say, remaining number which we arrived in after this division by 2 and division by 5, we will use for the experiment with the Gauss sum factorization. Then the remaining Gauss sums, which we will receive, is given by 2 to the power n2 times 5 to the power n2 times the prime decomposition which we have received from the Gauss sum factorization from the experiment. And this is actually the post-processed data set from the top. We actually can see that we don't see anymore these Gauss factors.
10 minutes, Rainer?
10 minutes, okay. So, so this we can do with, let's say, single qubits. Then we can actually also include, let's say, 2 qubits, which are shown here. In this case, they are in a copper cavity The reason for this is we have to induce a magnetic field to tune one of the qubits, because one is in a tunable qubits with two Josephson junctions in a ring configuration. And what we see here is actually the resonance of the, let's say, qubits, qubit 1 and qubit 2, if we change the magnetic field. This is the resonance frequency here. We see here very nicely, let's say, that these two qubits are coupled. And by actually applying microwave pulses, we can achieve a base state with a fidelity of about 83%. Of course, if you have two qubits, the first thing you want to do is you want to quickly check if quantum mechanics holds and do a Bain inequality measurement. In this case, we used a experimentally friendly protocol, the CHSH protocol, and have seen which actually measures the, let's say, correlations. We prepare base states and measure actually the correlations of the two qubits in various axes, as it's shown here. And the, let's say, protocol says that this correlation parameter is actually smaller than 2, assuming we, let's say, this hidden variable theorem will actually hold. And only if quantum mechanics is correct, this correlation parameter is larger than 2. So the experiment which we have done is actually shown here in this diagram below. We have these two qubits and generate a base state here. Then we are doing the rotations of these qubits and a state tomography, and later on the measurement of the qubit states. And indeed, what we are seeing is, to a certain extent, a let's say, some similarities between the theory and the experiments. And at certain places, actually, in fact, here, a violation of the local variable theory. Okay, so then I've shown you that we have, let's say, very good control over atomic systems or superconducting systems. Now, actually, it's the time to bring these two systems together. And this is shown here. So one could actually envision to use an atomic systems, for instance, as the quantum memory part, because it can have, in principle, extremely long coherence times, up to seconds, and the superconducting systems as the processor, which have extremely fast gate operation times in terms of gigahertz, which is not possible to do with atomic systems. And one way to actually bring these two systems together is by directly bringing these atoms very close to a superconducting qubit. In this case, for example, a Transmon Qubit. And we can actually see here very nicely on this picture, there are these two pads, which are this capacitor pad, the shunt capacitor pads. If you bring atoms in close proximity to the shunt capacitor pads, they will change the capacitance of these capacitors, because the direct constants can actually change. In fact, if we excite the atoms to Rydberg states due to the large polarizability of the Rydberg states, this let's say the direct constants of the medium between these two capacitor pads will change dramatically, and with this the resonance frequency of the qubit is changing. And we have actually shown theoretically that by doing so, we are able to transfer a state from the atomic systems to the superconducting qubit system. Very briefly, for example, this is the energy diagram of the superconducting qubit system together with the atomic system. if now the atom is in the ground state, we see this traced out red curve here, which I'll just trace out now. If we excite the atom to a Rydberg state, this curve will actually shift towards this direction here. So meaning by changing, or let's say by moving the qubit to this position here, we can actually induce a transition from the ground state to the excited state and then actually move back, only if the atom is in a Rydberg state. If it's not in a Rydberg state, it will just remain here because the transition frequency from the ground to the excited state would be too high for the atom if the atom would be in the ground state. And by doing so, we can actually show that using this type of circuit, we can transfer the atomic state to the qubit state and also vice versa.
5 minutes, Rainer?
Thank you. In the experiment, this looks as the following. So we have a atomic system here, normal magnetopical trap. We prepare there our atomic ensemble, move it along a vacuum tube into the dilution refrigerator to the base plate temperature, which is in this case about 40 to 70 millikelvin. Inside this dilution refrigerator, the vacuum pressure is extremely high, and which is also very useful. So we can actually do many experiments with the same ensemble of atoms. And we actually see lifetimes in the dilution refrigerator of about 700, or let's say roughly 800 seconds. Inside the dilution refrigerator, we have again a 3D cavity and a Transmon qubit. We actually move the atoms towards the Transmon qubit, and which the circuit diagram is actually shown here, how it actually looks like. So we move the atoms towards the Transmon qubit, and with this actually, depending actually in which state the atoms are, this will change the resonance frequency of the Transmon qubits, which again, at the end of the day, will shift the frequency of the 3D cavity where the Transmon qubit is coupled to. And the simulations we have done have actually shown that, let's say, also for moderate distances of the atoms to the Transmon qubits of, let's say, something like 50 micrometer, you would actually see a shift in the resonance frequency of about 20 megahertz, which we are, let's say, easily observable. Okay, so this is the current status. What we will actually do next is we will increase our capabilities for the superconducting circuits and move to, let's say, larger systems. So here's a chip which we have produced, which has 10 qubits. In this connectivity, you can actually see here, which we will first test in our superconducting systems and then maybe bring over to the hybrid system. Further, we actually then try to explore to maybe directly design chips with multiple qubits towards actually connecting atomic systems with superconducting quantum systems. So I hope I'm still in time. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Rainer. Very nice talk. So we have. So I suggest. So there are a few questions. So first, I suggest we go to Q&A. Rainer, maybe you can read the questions in the Q&A.
Okay, so there's a question from Andreas Osalo. Which says, I never saw the Ig Nobel Prize highlighted as you did in your talk. Usually I thought this is for something which has been considered by the committee That's funny to use less. Can you comment on this? Okay, so so let's say the experiment which we have done. So I didn't really went through in too much detail in the experiment. So the experiment which we have done is we wanted to actually know how magnetoreception in animals are working. And there are, let's say, two theories right now which try to describe this. So one is saying that magnetoreception is done by magnetite particles, so that there are small magnetite particles inside your animal and somehow attached to some nerves. And if you apply magnetic fields, this particles can actually move, and somehow the animal can sense this movement. And the other idea is in microreception, that's sort of a chemical process, this radical pair mechanism, that let's say certain type of reactions are faster in a magnetic field, on a certain aligned magnetic field to the molecule. And with this, let's say, experiment we have done is we could actually investigate this theory about magnetoreception with this magnetite particle. And what we have seen is, in this case, we used the American cockroach because that's quite common in our area where we're living, especially close to the canteens. We have used this animal because, let's say, there are other papers which actually suggest that the American cockroach can sense magnetic fields. There were some behavioral studies on this. And what we actually have shown is that, let's say, the dynamics of the small magnetite particles inside this inside the American cockroach are actually too slow to be used for magnetoreception. Let's say a little bit funny part on this is actually that we have also shown this for dead animals, and in fact, actually for dead animals, it's even much more slower. So that in this case, let's say dead cockroaches would be even, let's say, worse in sensing the, let's say, the direction of the magnetic field. And I guess this is sort of the twist why we received the Ig Nobel Prize for this. But behind this, I have to say, there's a let's say, quite serious body of scientific work.
Okay. So so Gerard has a question.
Thanks, Luigi. So there's a comment and a question. So first of all, Rainer, thank you very much for this wonderful talk. Another comment on the Ig Nobel Prize. So Sir Michael Berry is also a recipient of the Ig Nobel Prize in the year of 2000. So I think this is it's a prominent group of people who are in this meeting who have the Ig Nobel Prize already. But Rainer, the question I wanted to ask you, because you showed us this wonderful idea of having this hybrid system, of having the long-term storage in the atoms and the fast processing time in the superconducting qubits. But what I was wondering, how fast is the coupling between the two? Do you maybe lose a lot of time because the coupling between the atomic system and the superconducting system might be slow, so that the speed up in the processing will be lost because the coupling takes up so much time?
Yes, that's a fair question, I would say. True. So the, let's say, coupling between, let's say, atoms and superconductors will be on time scale of the atoms at the end of the day, which we are in the range of about, let's say, 20 megahertz, which we have seen where we have a coupling strength of about 20 megahertz. So it's actually not possible to, let's say, transfer the information from the superconducting systems to the atoms in gigahertz time scale. But we can actually store, let's say, the information inside the atom for a long time. Or what is actually, let's say, more important is, or let's say evenly important is, that we can actually transfer this to photons. This is actually not possible with superconducting devices, which are just working on the microwave regime. But yeah, so the coupling itself is one, let's say, on the speed up one of the bottlenecks, because we are using atomic systems, which is at the end of the day the bottleneck there. But so still, it's the reasonable numbers.
So you would use the atoms as sort of like the mediator between the photons and between the optical photons and the microwave photons.
So the atoms are very, very flexible, which I've shown, right? So if you can somehow couples, you can use atoms for everything. You can use them as a storage and as a mediator between, let's say, microwave and optical frequencies. Correct.
Good. Thanks.
There is a second question from Andreas. Maybe you can read.
Yes, sure. So how difficult is it actually to scale the Gauss sum experiment? That's also a fair question. Of course, this Gauss sum experiment is just a demonstration experiment of, let's say, how well we can actually control our single qubit system. It's actually not possible with this to encrypt larger numbers. In fact, actually, to calculate the phases you have to apply for your various microwave pulses, for your various pi microwave pulses, for this, you have to do the factorization by hand. So it's not really, or let's say outside, and then actually you have to do the factorization, the division of n over L, and with this you get the phase which you have to apply to the microwave pulse. So it's not really that you can, let's say, break any type of encryption with this system, because you're still relying on classical systems. If you want to break encryption, you have to use larger quantum computers, which I think will take a few years, at least.
Yeah, then there is another question by Tonia Pollaro.
Thank you very much. Thank you, Rainer, for your nice talk. And I'm Tonia Pollaro, and my question concerns the quantum state transfer experiment you performed between superconducting and atomic qubit. First, I assume it's a truly quantum state transfer, so not only transferring the one state, but also every superposition. So my question would be, what is the average fidelity that you achieve in this experiment? And the second question is if you are also performed the experiment scaling up the state transfer. So for instance, you showed the experiment with two superconducting qubits. If you tried the experiment by transferring a 2-qubit quantum state from the superconducting to the atoms. Thank you.
Okay, yeah, thank you for your question. Maybe just to clarify, so we have not done the experiment. So what I've shown is actually, maybe can I?
Sorry, I've seen then I misinterpret the figures with the probabilities and was thinking.
No. So what we have done is we have simulated it. We have done, let's say, based on our experimental setup, we have done a simulation. Let's say the state transfer probability, I think it was, so we have written a paper there, I think it was in the range of about 95%.
Oh, very good, thank you. So, so the second part has not been simulated then to transfer a 2-qubit state.
So yeah, so no, we haven't, so we didn't thought about 2-qubit states. So for this actually would, okay, that's, I think it's also a tricky questions. I mean, then you have, let's say, a tripartite system, and yeah, I think, yeah, so yeah, it's
so I was thinking at the experimental setup in which one puts the two atoms in the shunted capacitor. Instead of putting one, puts two atoms in two different superconducting qubits, so to have a simultaneous transfer of the complex state, if possible, say, from an experimental point of view. But thank you for your answer. Thank you.
Yes. Yeah, I think let's say the tricky part is the simultaneity of the transfer, because you have to talk to the 2 qubits at the same time. But yeah, it's an interesting question.
Yeah, it's a very interesting question anyway. There is a, I think we are late, but I mean, we have a last question by Joseph. So please, Joseph.
So thank you very much, Rainer. I enjoyed watching your presentation and this progress that you have Transmon Qubit alive in the dilution fridge, and you are moving atoms towards it. Yeah, it's really exciting. And I wonder if the lasers that you would apply for the Rydberg excitation would do any harm to this Transmon Qubit. Do you need to take special care of protecting it?
Yes. So any light close to the qubit is a problem. Or let's say any scattered light close to the qubit is a problem. So we have done, let's say, a few experiments where we actually looked at applied laser field and looked at the, in this case, changes in the 3D microwave cavity which we are using in terms of the resonance frequency. And if we apply, or let's say carefully adjust, let's say the laser field, that there's no overlap with the, let's say, metallic parts, then let's say there's also not too much light scattered, and we don't see any resonance or resonance shifts. However, it's sort of dramatic shifts you can already see when we, let's say, have just a few milliwatts of lights directly on the cavity. We haven't done these experiments right now with the Transmon Qubits in there with the light field, but this is on our bucket list.
Okay. How close do you need to go to the Transmon Qubit with the atoms?
It's about 50 micrometer.
50 micrometers, fine. So probably you work out with the laser beams.
Yes, it's sort of a technical issue. Yes, I mean 50 micrometer if you go to Rydberg states.
Sure, good, exciting. So.
Okay, so I think I would close the session now. Of course, who wants can stay, and but I would say today we are very late. So thanks all the speakers.